Hello. In the previous video, we studied definition of improper integrals, and we learned two integrals right here. So this is what we got from the previous lecture, right? And we use these two integrals to um, consider whether an improper integral converges or diverges, all together with the idea of similarity. And today we solve several examples just using the definition. Okay, let's consider the following one. We need to evaluate the integral from 0 to infinity e to negative x dx. So from the previous lecture, we see, yeah, this integral converges, right? And now let's use definition to show that. And what is antiderivative of this? So, we have only one improper point, so that is limit of b approaches infinity in here, integral from 0 to b, e to negative x dx, right? That is the definition. And antiderivative of e to negative x is negative e to negative x, right? Evaluated from 1 to b. And the limit when b approaches infinity, that is limit of the function negative e to negative b minus negative e to 0, right? So you have limit of, I write 1 over e to the b plus 1 when b approaches infinity, and this is just 1 because the limit of this guy when b approaches infinity is 0. So yeah, the limit exists and equal to 1, right? So we say, yeah, that's another way to show that the integral converges. But I tell you again, right, that is very simple case. So we are lucky because we may evaluate the antiderivative of this function. Okay, so if you cannot evaluate the antiderivative, there's no way to use definition. That is the thing. All right, let's consider another example. Say integral from 0 to infinity dx over x squared plus 1. So this is well known, right? I can write limit when b approaches infinity, integral from 0 to b dx over x squared plus 1, because 0 is not an improper point, so that's fine. We have infinity only. And what is this? This is arctangent, right? Arctangent of x evaluated from 0 to b. So I write here the limit of arctangent of b minus arctangent of 0 when b approaches infinity. So what is arctangent of 0 is 0 already. So that is just arctangent of b when b approaches infinity. So what's that? Look at this unit circle. So this is tangent a6, right? The tangent a6. When b approaches infinity, that means the value, right? That is the function value, arctangent. Is that correct? Arctangent is the function value. When the function value b in here, when b is the function value, b is the function value, right? In order to find the angle, so you need to connect that point with the origin, and here is your angle. But this guy just approached positive infinity. So that means when this guy approaches positive infinity, this guy approaches pi over 2. Right? So this is just pi over 2. And of course, the integral converges. That's how we can use, definition. Let's consider another one which is more complicated. Let's evaluate the integral from 1 to infinity 1 minus x e to negative x dx. Interesting. So you might break this function into two functions, right? From 1 infinity e to negative x dx, and then minus 1 infinity x e to negative x dx. How to say about, convergence, divergence of this function if we want to use similarity. So let's do that first, right? Before we evaluate this, because otherwise, if the integral diverges, so that is just infinity. Is that correct? So you might think about, this function is 1 minus x over e to the x, and the proper integral is the proper point is just infinity, and we know that at infinity e to the x is very big, right? So you might compare with x cubed. Is that correct? So you might compare with x cubed, and then you might just consider the absolute in here, right? So because you have 1 minus x, so you might compare this with x cubed, and we say, yeah, 1 minus x over e to the x absolute is less than 1. It just, even I can write just 1 minus x and x cubed. And you consider similarity, because 1 is just a constant, so you don't care about that, right? And this is similar to, x over x cubed, which is 1 over x squared. And this function, if you integrate this function, from 1 to infinity dx over x squared, so we know this is just a finite number, right? Because the power p in this case is 2, bigger than 1. So basically, yeah, we use similarity, and we just show that our integral converges. So that is a finite number. Is it okay? So if that is a finite number, so we just go ahead to find that, if possible. Okay. So I break the integral into two integrals. Let's denote by I1 and here by I2. Let's find I1. The I1 is easy because we know antiderivative of e to negative x. That is, e to negative e to the x, right? We just saw that. And then, you consider the limit in here. When b approaches infinity, evaluated from 1 to b, right? We just solve this integral. So that is limit of, negative 1 over e to the b minus plus 1 in here. B approaches infinity, and that is just 1. So the first integral is 1. Let's find the second integral. So I2 is the limit when b approaches infinity from 1 to b x e to negative x dx. And in order to integrate this function, we need to do integration by part. Is it correct? Because you have x and e to negative x in here. So we learned that. Now, in such situation, we need to do by part, right? Integration by parts. Okay. So I will put u equal to x. Because when I differentiate this, one time x will disappear. And dv is e to negative x dx. From here I get du is just dx, and v is negative e to negative x. To antiderivative of e to negative x, right, is negative e to negative x. Then the integral I2 is equal to, let's find, antiderivative. Sorry, I don't want to be confused. So antiderivative of x e to negative x dx is equal to negative x e to negative x, right? uv minus v du, right? Minus with the negative would be plus, because we have negative in here. v du is e to negative x dx. So you can write negative x e to negative x minus e to negative x plus c. So that is antiderivative. Now you can evaluate integral from 1 to b. Then I2 is the limit when b approaches infinity of negative x e to negative x minus e to negative x, evaluated from 1 to b. Then this is equal to limit, at b you have negative b, I can write, like this, e to the b minus 1 e to the b. Okay, I just flip that, right? We have negative, so I just, and then minus, let's say, what is that? Minus, I plug 1 into this, so I get plus, right? We have negative with negative, so plus e, and then plus e. Interesting. Is that correct? At 1 you have 1 right here and 1 right here. Yes. So the first two terms approach 0. This guy approaches 0. This guy also approaches 0. Why? Of course you might use L'Hopital rule, right? You differentiate that. But again, you might use similarity, because at infinity exponential function is very fast, much faster than polynomial, so the limit is just 0. Okay, or you might use L'Hopital rule, I repeat again, right? So you have 2e. Interesting. So what do I get? I2 is 2e, I1 is 1, so I think we don't have to break the integral into two integrals. We may use integration by part right from the original one. Okay, so I have to do integration by part. As we learned that, because when you have something x in here with e to the negative x or e to the x, we need to do integration by part. So I put u equal to 1 minus xn dv equal to e to negative x dx. Okay, from here I get du is negative dx and v is negative e to negative x. That is antiderivative of e to negative x. And by the formula of the integration by part, I have the antiderivative of 1 minus x e to negative x dx equal to negative 1 minus x e to negative x minus antiderivative of this dx. But you have negative with the negative and then minus, so you have negative in here, right? E to negative x dx. And again, what is antiderivative of this? That is negative e to negative x, right? And then you have negative this, negative 1 minus x e to negative x. So you have, negative e to negative x plus x e to negative x, and then plus e to negative x. These two guys will be cancelled out, and at the end you have only x e to negative x plus constant. But the constant is, is okay, because we need to evaluate definite integrals, right? Now I can find definite integral from 1 to infinity 1 minus x e to negative x dx is equal to limit of integral from 1 to b 1 minus x e to negative x dx, and that is the limit of what? Of the function x e to negative x evaluated from 1 to b. Right, and then you plug b and 1 into the function, you get limit of b over e to the b, I write this way, okay, minus 1 over e, because e to negative 1 is 1 over e when b approaches infinity. All right, so the limit depends on this term. But again, right, when we study limits and L'Hopital rules, and we just recently learned in the previous video, we know exponential function is very big if you compare with polynomial. So, whatever you have in here, even be 1,000 or 1 billion, whatever you have, you divide by e to the b, that will approach 0 as b approaches infinity. So, this limit is just 0. I mean, the limit of this guy at infinity is just 0. Does that make sense? So, that means, the limit is just negative 1 over e. Of course, you may use L'Hopital rule to consider the limit of, b over e to the b. Because this is of the form infinity over infinity. So you might differentiate the top and the bottom, right? You get 0 right away. But again, right, we know singularity. So I accept such solution. You just write me at infinity. This guy is very big, so if you compare with the, with the b. So the limit is just 0. Okay, just ignore this, okay? Just b over. But, even you have b 1 million divided by e to the b. That also approaches 0. So the limit is equal to negative infinity. Why? Why is that? Why you have negative in here? But that is reasonable because the function 1 minus x times e to negative x is less than 0 on 1 infinity. Right? So you have negative area. This is 1 minus x e to negative x is less than 0 on negative 1 infinity. On 1 infinity, sorry. So that means the graph of this function, I don't know, somewhere in here, right? But, it just below the x-axis. So that's why the area in here is negative. Right? So that's it. That's how we can, evaluate such integrals. Let's move to another example. Let's consider the integral from negative infinity to positive infinity, ex dx over 1 plus e to 2x. We have e to the x, right? And then in the bottom you have 1 plus e to 2x. So probably you may guess, something u squared in here, right? If you put u equal to e to x. Is that correct? So it's okay. That's the first thing, right? So you might think, yeah, you have that. The second thing is, of course, you need to see if the integral converges or diverges. So how do you think about that? Converge or diverge? I think that converges. Why? Because you have e to the x on the top, but in the bottom you have e to 2x. And you know that exponential functions, approach infinity very fast. And you have square in the denominator. So that is why, at negative infinity and positive infinity, maybe, the integral is just a finite number. It's just converse, right? There's no way to be diverse. Does that make sense? So, that is my, it's my guess. So if you want, you might prove that, right? But, that is my guess. So since we have negative infinity and positive infinity are improper points, we need to break this integral into two integrals. Let's do this. So that is negative infinity to 0, e to x dx over 1 plus e to 2x plus 0 to infinity e to x over 1 plus e to 2x. So now I do substitution. I put u equal to e to the x, and then from here I get, du is e to the x dx. So my integrals will look like, let's find antiderivative, right? Because the function is the same. So ex dx over 1 plus e to 2x is just, du over 1 plus u square, and that is arctangent of u plus c. So, I apply this function for negative infinity 0 and 0 infinity. I have integral from negative infinity to 0 e to x dx over 1 plus e to 2x is just limit b approaches negative infinity arctangent of e to the x, because here you need to plug e to the x back here. Okay, so evaluate it from negative infinity to 0, and that is from b, sorry, and that is the limit of arctangent of e to 0 negative infinity in here minus arctangent of e to b, right? E to b. So I have limit of arctangent of 1 minus arctangent of e to the b when b approaches negative infinity. So b is less than 0. You see this? B is less than 0. So I can write this as arctangent of 1 over e to negative b. Is that correct? And this value just approaches 0 when b approaches negative infinity. So arctangent of 0, again, the whole thing approaches 0 in here. So the limit is just arctangent of 1, which is pi over 4. So that is the first integral. Similarly, we may evaluate the integral from 0 to infinity ex dx over 1 plus e to 2x. That is a limit when b approaches infinity arctangent of e to the x from 0 to b. Right? So I can write that is the limit when b approaches infinity arctangent of e to b minus arctangent of 1, right? Because it's 0, so I have arctangent of 1. All right, we know arctangent of 1 is pi over 4, right? So minus pi over 4. How about arctangent of e to the b? Again, when b approaches infinity, e to the b approaches infinity. You see that? And as we have seen, for tangent, when the value just approaches infinity, right, the angle will approach pi over 2. So this approach pi over 2. That means the limit is pi over 2 minus pi over 4 equal to pi over 4. So you have two integrals, right? Each of them approach or equal pi over 4. So the original equals pi over 4 plus pi over 4, which is pi over 2. So let's solve this problem real quick. We have the unit circle in here. We want to show that the circumference is 1. So I just need to consider just 1/4 of the circle, right? So that means x is from 0 to 1. And for this part, I can solve y equal to square root of 1 minus x squared, because y is positive, right? So regarding the integral, the formula of for the arc length, I have integral from 0 to 1 square root of 1 plus y square, y derivative square dx. Okay, that is the arc length. And y prime in this case is 1/2. I use the chain rule minus x squared to negative 1/2 times negative 2x, which is negative x times 1 minus x squared to negative 1/2. And then I plug y prime into this formula. I get the arc length is equal to integral from 0 to 1, 1 plus square of the y prime. So I have x squared over 1 minus x squared dx. All right, when you square this function, so you have negative 1. When you flip that, you get 1 over 1 minus x squared. So I get 0, 1 in here, and then square root of 1 minus x squared plus x squared over 1 minus x squared dx, and that is just 0 to 1 dx over square root of 1 minus x squared. And we know this, right? That is a cosine. No, arc sine, sorry. So we have arc sine of x evaluated from 0 to 1. Given that the integral is improper because the integrand function is not defined at 1, right? But we know the antiderivative, so you just need to consider this. So that is the limit of what? Of arc sine of x evaluated from 1 to b, right? When b approaches 1. So you have arc sine of limit arc sine of b minus arc sine of 0 when b approaches 1, and then this guy is just 0, right? So what is arc sine of b when b approaches 1? Look at this. So you have, here is the sine axis. B approaches 1 means the function value, right? The function value approach 1. So when b is right here, b approach 1 is mean right here, so that means the angle E is approaching just pi over 2. So that is pi over 2. So see, 1/4 of the circumference is pi over 2. So circumference should be 4 times of pi over 2, right? And that is just 2 pi. All right, so I think we finished our video in here, okay? And that's how we finish this chapter. So we'll do a short review shortly, and we have tests on this. And the next chapter would be very long, very difficult, and very new for you. But again, the idea of similarity and improper integrals will be very useful in the next chapter. All right, thank you and see you.